Imagine a switch that simply refuses to do what you tell it. You flip it on, and the lights go off. You flip it off, and the lights blaze on. It sounds like a broken gadget, or maybe just a really stubborn friend, right? But in the world of digital electronics, this rebellious behavior isn't a flaw. It is the absolute foundation of modern computing. What if I told you that by simply learning how to say no, a circuit gains the power to make decisions? Welcome to Physics in Motions. Today we are decoding the magic of logical inversion. In digital electronics, this opposite maker is called a NOT gate. You'll often hear engineers call it an inverter. Why? Because its entire purpose in life is to invert the signal you give it. The basic idea is beautifully simple. The output is always the exact opposite of the input. If you feed it an input A, the output becomes not A. Let's look at the truth table to see this in action. Digital systems speak in a language of ones and zeros. If input A is 0, the output is 1. If input A is 1, the output is 0. But what do 0 and 1 actually mean in the real physical world of wires and circuits? In a standard system, a 0 represents a low voltage, usually 0 volts, which means off. A 1 represents a high voltage, usually plus 5 volts, which means on. So feeding plus 5 volts into a NOT gate gives you 0 volts out, and feeding it 0 volts gives you plus 5 volts out. But how does a circuit actually do this physically? Let's look at two brilliant ways to build. Before microchips, early computers used mechanical switches called relays. Let's look at the relay equivalent circuit for a NOT gate. Here, we have a relay coil, let's call it K, and a switch that is normally closed. This means when the machine is just sitting there doing nothing, the switch connects a plus 5 volt supply straight to our output, B. Case 1. Let's apply plus 5 volts to our input A. When we do this, electricity flows through the relay coil. The coil energizes, acting like a magnet. This magnetic pull violently yanks the switch open. The connection to the plus 5 volt supply is broken. With no voltage reaching the output, output B drops instantly to 0 volts. We put a 1 in and we got a 0 out. Case 2. Now, let's drop input A to 0 volts. The coil loses its power. The electromagnet turns off. Because it's a spring-loaded, normally closed switch, it snaps back into its resting position. The path is restored. The plus 5 volt supply rushes across the switch, and output B becomes plus 5 volts. We put a 0 in, and we got a 1 out. The output is always the opposite of the input. Relays are great, but they have moving parts. They are slow and bulky. Modern computers use solid-state electronics. Let's upgrade our NOT gate using a transistor. Look at this equivalent transistor circuit. We have a transistor acting as our digital valve, a resistor at the top, our plus 5 volt power supply called VCC, and our output node B sitting right between the resistor and the transistor. Case 1. Let's apply plus 5 volts to input A. This turns the transistor fully on. It acts like a wide open pipe. Suddenly, maximum current rushes down from VCC straight through the resistor and down to the ground. Because current is flowing heavily through the resistor, all 5 volts are dropped or used up across that resistor. By the time the path reaches our output node B, there is no voltage left. Output B becomes 0 volts. Case 2. Now let's apply 0 volts to input A. The transistor turns fully off. It becomes a brick wall. No current can flow down to the ground. Because there is 0 current flowing through the resistor, it doesn't drop any voltage at all. So the full plus 5 volts from VCC pushes right past the resistor and sits entirely at output B. Output B becomes plus 5 volts. So we can build it with magnets, and we can build it with silicon. But how do we write it down on paper? In Boolean algebra, the mathematics of digital logic, the NOT operation is a complementation operation. Its symbol is a simple overbar over the letter, We write it as bar A and pronounce it a bar or not A. The math is as simple as the circuit. Bar 0 equals 1 bar, 1 equals 0. And here is a fun mental trick. What happens if you put two NOT gates back to back? If you invert an inversion, you cancel it out. Double inverting a signal simply gives you the original signal back. A bar equals A. It's like saying, I am not going to the store. It just means you are going. Let's step back and look at the deep visual intuition here. Why does inversion happen in both of these totally different circuits? In the relay circuit, inversion happens through switch logic. Supplying power creates a physical action that intentionally breaks the path of another power source. The presence of an input physically blocks the output. In the transistor circuit, inversion happens through current control and voltage starvation. Turning the transistor on opens a trapdoor to the ground. All the electrical pressure rushes down the drain, starving the output node of its voltage. In both cases, giving the circuit an input triggers a mechanism that steals the power away from the output. Let's summarize what we've uncovered today. First, a NOT gate always gives the exact opposite output of what you feed into it. Second, a relay can implement this mechanically by using an electromagnet to pull open a normally closed switch. Third, a transistor can implement this electronically by creating a shortcut to ground, dropping the voltage before it reaches the output. And finally, Boolean algebra represents this mathematically using an overbar, where bar 1 equals 0 and bar 0 equals 1. Computers may seem impossibly complex, but at their very core, they are just millions of tiny, stubborn switches, constantly flipping the script and saying, no. Thanks for watching Physics in Motions. Stay curious and keep visualizing the invisible.